In a few moments, I'm going to actually start talking about finding global or what we call absolute extrema. So being able to use the derivative to find um, the absolute extrema or absolute maximum or absolute minimum of a function. So we'll talk about about that in a moment. But I thought it might be helpful to just first, again, make sure that we're pretty solid on the first derivative test because we're really just going to be extending that. And just again, just make sure that we understand why this indeed works. I just want to make sure we have a good intuition and understanding as to why finding out where our derivative is positive would make the most sense. So again, if for example, I had something like a parabola, for example, like x squared, well, visually we can see it's pretty obvious that we have a relative minimum here at x is equal to zero, at x is equal to zero. But ask yourself, what's happening with the slope of our tangent lines leading up to that? We see that the slopes of our tangent lines here are negative, right? We can say that f prime of x here is negative, or write something like this, is less than zero here, right? AKA the function is decreasing. And after x is equal to zero, the slopes of our tangent lines are positive. The first derivative here is greater than zero, aka our function is increasing. So we can see here that there's been a change in behavior. Whenever there's a change in behavior, that is a prime candidate for where there may be an absolute, or an, excuse me, a relative extrema. In this case, we have a relative minimum. Here it's relatively the lowest place compared to the points immediately before and after. So let's try another problem here with this, just make sure that we're pretty solid on this before we start talking about global extrema. Let's try this problem here, okay? Because I also want to highlight something that's interesting that comes out of this. First off, the first thing I always want to do before I do the first derivative test is ask myself, are there any domain restrictions? Are there any places where this function is undefined? Because that could potentially be a place where a function changes behavior. Again, it would not be a critical number or a potential candidate for a relative extrema, but it's still important to know. So are there any domain restrictions here? And the answer is no. There are no domain restrictions here. This is a polynomial function. The domain is all real numbers, so we're good there. So now let's jump into finding the derivative of this function here. So the derivative of this function, pretty straightforward, just using the power rule. We can say 3x squared minus 6x plus 3. Now, we're going to set our derivative equal to 0. We're going to now start finding some possible critical numbers here. We're going to find some critical numbers, okay? So again, a critical number is where the derivative could be equal to 0. Let me move this back up here. It's where the derivative could be equal to 0, or where the derivative could be undefined, where the derivative is equal to 0 or the derivative is undefined. So first off, let's set our derivative equal to 0. And we can easily factor out a 0 and divide out a 3, I should say. So this would be this. And this should be pretty easily factorable. So we see here that x is equal to 1. Therefore, one of our critical numbers here is x is equal to 1. Now let's check. Is there any place, any x value that would cause this first derivative to be undefined? And the answer is no. So the only critical number that we've been able to find is where our f prime of x is equal to 1. So we just need to test two intervals here. So what we're going to do is we're going to plug in a number that's less than 1, plug in a number that's greater than 1, see their signs, and check to see if there's a change in behavior. So if we try plugging in a number that's less than 1, so for example, 0 would be a great candidate, f prime of 0 here, you don't have to write this down, but it might be a good idea to check. We see it's going to be equal to 3. Therefore, let me do this in blue. This is going to be positive. Therefore, my function is increasing here, okay? Now let's try plugging in a number that's greater than 1. And you can do this mentally. I'm just going to kind of actually do that. F prime of, let's say, 2. Well, that's 3 times 4. That's 12. Minus 24, that's negative 12 plus 3. That's going to be, excuse me, 2, that's 12, 24, is that. And that should also be positive as well. So we see that this is indeed also positive, right? Something that could have been easier for you is to just go ahead and plug that into this factored form. That would have made your life a lot easier. So 2 minus 1 is 1, 1 squared is positive. So check this out. This function continues to increase, and it kind of looks like a funny face while we're at it. This function now, we see, continues to increase. So what does that tell us? Pretty important. First off, it tells us that there is no relative extrema. There is no change in behavior, right? Our function continues to increase. Therefore, we would say that this function is increasing over the interval negative infinity to infinity. It is decreasing where? Never. And on top of that, it's important for us to note that what type of function is this? We can describe this function as a function that is monotonic, one that strictly increases or decreases. This is an example of a monotonic function. It stays in one type of behavior as constantly increasing or constantly decreasing. So from this, there are two important notes that I want to highlight. So two notes, and I'll just briefly mention them here. First off, not every critical number produces a relative extrema. Okay, so just because you have a critical number does not guarantee that there is an relative extrema there. Okay. Secondly, and on that note, even though the slope at x is equal to 1 is 0, this function is always increasing. So it's kind of a continuation of the first point. Just because you have a horizontal tangent line at a specific point does not guarantee that there will then be a change in behavior. Okay, so I think this is a great problem to highlight these two important notes and things to keep in mind as you're finding extrema. So with that said, let's actually move on to talking about relative extrema. So, excuse me, absolute extrema. And another name for absolute extrema is global extrema as well, right? So the idea behind global extrema is essentially all we're doing now is we're extending our first derivative test to something called the candidate test. That is to say, we can now include endpoints. So the thing about a global extrema, its definition is different. Refer back to my previous video on this, but for something to be a global or absolute extrema, it doesn't have to be greater than the point immediately before or after. We can look at global extrema over a closed interval. So even if it's the very first point in a function's domain, we can still include it as being an absolute extrema if it is the greatest point or the greatest y value over its entire domain. So you'll notice here that this candidate test is very, very similar to the first derivative test. In fact, if you want to jot these down or take screenshots and compare them, you'll see that they're pretty similar. The main thing is now we are including the endpoints as a possible candidate for our absolute extrema. So let's do an example together where we're going to use what we call now the candidate test to determine the absolute extrema of the function over the interval from 2 to 6. So let's look at this function here. Okay. First things first, we're going to look at our function and see if there's any domain restrictions, and the answer is no. I'm just going to write that to the side. There are no domain restrictions here. This is a cubic function, aka some type of polynomial function, so our domain is going to be all real numbers. Okay, so I don't have to worry about any domain restrictions. Now let's jump to finding the derivative. So the derivative of our function is going to be, see, if I apply the power rule, 3 times 1/3, so that's going to be x squared minus 4x. Now I'm going to see where my derivative might be equal to 0 or where it might be undefined. Let's start with 0. If I set my derivative equal to 0, I can factor this as such and see that I've got one set of critical numbers at x is equal to 0 and 4. Then I would look at any possible places where my derivative is undefined. And again, just like I mentioned earlier with the original function, I've got a polynomial function as my derivative. Its domain is all real numbers. So there's no value of x that would ever cause this to be undefined. Now, before I proceed, I want to highlight here that our interval that we're looking at this is the closed interval from 2 to 6. For this reason, I don't want to include 0 as one of my critical numbers. It is outside of the interval that I'm looking for. Could it be an absolute extrema if I were to expand out my interval? It could, but I'm not really worried about that right now. So since 0 is not in my interval from 2 to 6, I'm not going to include that as a critical number. So if I were just doing the first derivative test, I would just be looking at 4 and choosing a number before and after. However, because I'm now looking at absolute extremas, I can now include my endpoints as possible candidates. So I'm going to label this as, well, I should maybe just use these markers here, as 2 and 6, and choose a point specifically within these intervals here. So if you were to just plug in a point, for example, something like 3 times -1, plug that into our first derivative, we see that this is going to be negative. Therefore, our function is decreasing there. Choose a number between 4 and 6, like 5. 5 times +1 is positive. So this function is increasing here. So we can say pretty confidently that there is a relative minimum at 4, but we're not worried about finding relative extrema right now. So we have a possibility of there being an absolute extrema or absolute minimum at x is equal to 4. So I'm going to note that. So let's write the candidates for our absolute minimum. And what is our candidate for an absolute minimum? We would say 4 right here. Let's find out what that is. F of 4. And in fact, this is the only possible candidate for an absolute minimum. Since the function is increasing after 4, there's no value there that's going to be less than what f of 4 would produce. And since it was decreasing up until x is equal to 4, you know that there's no point, again, that would ever be lower than that as well. So our only candidate is f of 4, our only candidate would occur at x is equal to 4. Since we're finding an absolute extrema, we want to state the y value. So we're going to evaluate our original function at 4. So 1/3 times 4 cubed minus 2 times 4 squared. And let's see, that should come out to 16 over 3, 64, or 64 over 3. This should be -32 over 3. I'm pretty sure that's correct. Okay, so our absolute minimum, we would say, is -32 over 3. We're not listing a coordinate, we're listing the lowest y value within this interval of this function. Now, let's look at candidates for the absolute maximum. Candidates for the absolute maximum. Well, where are my potential candidates? I've got one potential candidate here at this endpoint and one potential candidate here. So what we're just going to do is we're going to see which of these points are greater. So we're going to look at f of 2. We're going to evaluate the function at f of 2, which is 1/3 times 2 cubed minus 2 times 2 squared. And let me check that, that's 8 over 3, common denominator. Okay, so that would have to be -16 over 3. Then let's look at f of 6, the other endpoint. Let's see, that would be 1/3 times 6 cubed minus 2 times 6 squared, and 216 over 3. That is actually going to give us 0. All right, so think about this for a second. So which of these points is greater or produces a greater y value? And the answer is f of 6. So instead of writing the coordinate, we are going to say that the absolute maximum occurs at, or the absolute maximum not occurs at, the absolute maximum is 0. Okay? So the candidate test, as you can see here, is really just a few steps beyond the first derivative test. We're now including the endpoints, and when we're finding absolute extrema, we're not concerned with necessarily just finding the coordinates, but the greatest or the lowest y values.